Without using technology, sketch the graphs of y equals 2 sine x and y equals minus 2 sine x for x between 0 and 2 pi. Right, so just one cycle. If you think about it, say f of x equals sine x is in the parent function. F of x equals sine x, well then 2 sine x must be 2f of x. And if you think of the transformation involved in turning f of x into 2f of x, this is a stretch, it's a vertical stretch, which means the invariant line is the x-axis. So stretch, you'll sometimes see it called a stretch parallel to y-axis or something like that, but I think the most useful way of defining it is stretch x-axis invariant, and the scale factor is 2. I think if you define it like that, then you can just look at what you're doing and actually use the line as the basis for your stretch. So I think it makes things a lot easier. So what I'm going to do is draw the parent function. Y equals sine x, or f of x equals sine x just does this. So it has goes up to 1 and down to minus 1, and this is 0, 2 pi, pi by 2, and 3 pi by 2. Okay, so that's the parent function sine x. Sine x. So then if we do this stretch, so what I mean about the invariant lines, you find the x-axis being the invariant line, and then what we can do is just use that. So this, with this vertical movement that we're doing, vertical stretch that we're doing, basically all of the distances from the invariant line are going to be doubled. So we had a maximum before of 1, that's going to go up to 2, so 1, 2. 2 like that. We had a minimum value of minus 1, that's going to have to be doubled as well to minus 2. And then if you think about it, you're just looking at the perpendicular distance to the x-axis for all key points. So if we take this point here, well, that is on the x-axis, so when we double that distance from the x-axis, you're just doubling 0. If we take this point here, which the perpendicular distance to the x-axis is 1, we're going to have to double that distance, so it's going to get stretched to here. We're back on the axis, so that doesn't move. This point here was at minus 1, so that's going to be doubled to minus 2. Remember, it's perpendicular distance to the invariant line. And this point here is on the x-axis again, so your y equals 2 sine x, or f of x equals 2 sine x, is going to go something like this. I mean, we could have picked a lot more points. Something like that. So this now is 2 sine x. Okay, so it's a stretch. You will often read about the amplitude, changing amplitudes at the height of a wave. So it was 1, now it's 2. There you go. So that's the vertical stretch. We've also been asked to sketch minus 2 sine x. So if, say, f of x, our parent function again. In fact, I might even make the parent function the 2 sine x that we just used, but you don't have to. 2 sine x, so minus 2 sine x would be minus f of x. So the reason why I'm doing that is because hopefully you can then see it's a special kind of stretch. So we still have the x-axis as the invariant line, but because you've got a negative scale factor, you actually go backwards as well. So it's often described as a reflection in the x-axis. That's what we're going to do. When I say reflection, we're going to reflect the 2 sine x, not the sine x. If we had the sine x, we'd have to, yes, reflect, but also double the distances, the perpendicular distances from the invariant line. But if we had 2 sine x initially as the parent function, then this would be a reflection in the x-axis, which is a special type of stretch. it's a stretch with an x-axis. The x-axis is the invariant line, and the scale factor is -2 if the parent function was sine x, which means you go backwards twice as far. So that's okay. So if we just draw the function, we've got 0, pi, 2 pi, pi by 2, and 3 pi by 2. We have to go up to 2 and down to -2. But if you think about it, we flip the thing upside down, so this point here will be reflected down to here. So we're going to have a point down here. And this point at 3 pi by 2 that was -2, well, that's going to be reflected up to 2. Like I say, you could have just gone straight from sine x, but because we already had it drawn, might as well use it. Anything that was 0 already, well, when you reflect it, that's not going to move. So that point, and that point will not move. And then you can just start to draw the thing. Something like that. So this is y equals -2 sine x.